Chapter 2, Section 1, Solving Polynomial Equations and Finding Zeros of Polynomial Functions. In Chapter 1, we devoted our studies to studying linear functions and quadratic functions, basically degree 1 functions and degree 2 functions. In this chapter, we'll be focusing on polynomial functions, mostly of degree 3 and higher. Let's start our discussion with a definition of a polynomial. A polynomial is a sum of terms whose variables have whole number exponents. So what's really important is that you remember that whole numbers are positive only, and they're positive whole numbers. So no negatives, no fractions, no decimals as the exponents. The coefficients of the variables can be any real number, but it's the exponents that have to be whole numbers. Here are some examples that you can look at. This is a polynomial because all of the exponents are whole numbers. 3, 2, and 1. When there is no exponent written, it's assumed to be 1. So 3, 2, and 1, those are whole numbers, so this is a polynomial. There are 1, 2, 3, 4 terms in this polynomial, and the highest power or the highest degree is 3. So you would actually call this a cubic polynomial. The next polynomial, you can confirm that it's a polynomial. Look at all the powers or the exponents: 4, 3, 2, and 1. Again, all whole numbers. So this is a polynomial of 1, 2, 3, 4, 5 terms here. The highest power is 4. Or highest degree is 4. So it would be a quartic polynomial. This is a 3-term polynomial. It would be a trinomial of degree 5. I forgot to write that down for you here. So degree 5 there. So this is a quintic for degree 5, a quintic trinomial. All right, so the first thing we're going to do is we're going to solve a polynomial equation. Now notice that this polynomial equation, first of all, is set equal to 0. And the next thing that you want to notice is that this polynomial is already factored. So what we can do is use a zero factor property. Sometimes people call it the zero factor rule. But you want to take the zero factor property and set each factor equal to 0 and solve. The zero factor property says that if the product of factors is 0, then one of the factors must be 0. So what I'm going to do here is add 1 to both sides. Over here, I'm going to add 4 to both sides. So those solutions are 1 and 4. For the one in the middle, I'll subtract 3 from both sides. And then I will divide by 2 to give me negative 3 halves. And we're done. I'll write these solutions in set notation. So I'll write negative 3 halves, comma, 1, comma, 4. Although I wrote these solutions in order from least to greatest, please don't feel obligated to write them in any order. Order does not matter in set notation. All right, so this equation was not that difficult to solve for x, and the reason is because this polynomial is already factored. All right, check out this next example. It's a polynomial equation. On the left-hand side, it's a trinomial because there's 3 terms. The highest degree is degree 5, so I would call it a quintic trinomial. It's set equal to 0, which is good, but it's not factored, so that's what you and I want to focus on doing right now. So please notice that the GCF is x cubed, so let's factor that out first. When you factor out x cubed, you're left with 2x squared minus 7x plus 5. Don't forget this is equal to 0. Let's continue factoring. The resulting trinomial factors as 2x, let's see, and then this has to be an x, both of the signs are going to have to be negative. I know that because in order to get a positive product here, the signs have to be the same. The middle coefficient's negative. That tells me they both have to be negative. In order to get negative 7x as middle term, 5 would have to go there, and 1 would have to go there. Now that you have completely factored, you can set each factor equal to 0. All right, so this one here has 3 copies of x, right? It's x times x times x is equal to 0. There's no need to set each one of those factors of x to 0. For example, x cubed is x times x times x is equal to 0. There's no need to set each one of these factors equal to 0 like I'm doing right now. That's a little bit redundant. It's too much. All you need to do is just set one of those copies equal to 0, and that's it. So let me actually erase all of that, and whenever I have something like this, a factor set to the power of 3 like this, I'll just take one copy of that factor and set it equal to 0. Here I'm going to add 5 to both sides, so I'll have 2x is equal to 5, and then I'll divide by 2, so 5 halves. And over here, of course, we'll add 1 to both sides. So you get x equal to 1. And then in set notation, it would be 0, 5 halves, and 1. I did not write these solutions in order from least to greatest. After all, 5 halves is greater than 1. But so it doesn't matter the order in which you write your solutions in set notation. This next equation is also polynomial. But the thing I want you to really notice is that this is not set equal to 0. So let us move all of the terms to one side and set this equal to 0. So I want to leave the leading term. Remember, the leading term is the one with the highest power, which is here, x cubed. I want to leave that positive, right? The leading term positive. So let's leave these two terms right where they are. And let's bring these two terms to the left-hand side using subtraction. So then when I subtract 2x squared and 9x from both sides, and I write the polynomial equation in descending power order, I get x cubed minus 2x squared minus 9x plus 18 is all equal to 0. The next thing I will try to do is to factor. Because this is a polynomial of 4 terms, I will try to factor by grouping. So I'll remind you, factoring by grouping uses the associative property of addition that says that the grouping of the addends does not change the sum. I usually put the first 2 terms in a group, and then the last 2 terms in another group. So I'll do x cubed minus 2x squared in a group, and then I'll put negative 9x and positive 18 in a group. Keep in mind that you could group these terms differently if you like. Also keep in mind that the sign in front of the term belongs to the term, so make sure you put the negative with the 9x inside this group. The next step in factoring by grouping is to factor out the GCF from each group. For this group, it'll be x squared, leaving you with x minus 2. In the next grouping, you should factor out a negative 9. If you factor out a negative 9, you'll get x minus 2 as a result. Now, we know we're on the right track here because this binomial factor matches this binomial factor. If for whatever reason that were not so, then we either did something wrong or we just need to change our grouping. All right, so we're going to continue. The next step is to factor out the common binomial factor, which is x minus 2. And then what remains when this common binomial factor is factored out, what remains is x squared minus 9. All right, set equal to 0. Now, you could set each one of these factors equal to 0 and solve right now. Or, if you'd like, you could factor this difference of 2 squares further. A difference of 2 squares factors as x plus 3 and then x minus 3. Okay? Now that this is fully factored, we can set each factor now equal to 0. And solve. Here, after adding 2 to both sides, you get 2. When you subtract 3 from both sides, you get -3. When you add 3 to both sides, you get +3. In set notation, I will write my solution as follows, my solution set. +2, and then +3 and -3 can be written using shorthand notation. It's actually double sign notation, plus or minus 3. Here, if you did not want to factor this further, you could have just set x squared minus 9 equal to 0. Add 9 to the right side, and then use a square root property to solve for x. It would have led you to 3 and -3. All right, example 4 changes the language of this kind of work. It says find the zeros of the polynomial function f of x is equal to x minus 2 quantity squared times x plus 3 times 7x minus 1. So what do they mean when they say find the zeros of this polynomial function? Well, what's really important to know is that the zeros of a polynomial function are the solutions of the polynomial equation. So if they want you to find the zeros of the polynomial function, all we have to do is take this function and set it equal to 0 and then solve. The solutions of this polynomial equation are the zeros of the polynomial function. So you can see, oh, we've been doing this work all along in this lesson. So when we find the solutions of a polynomial equation, we are in essence finding the zeros of the polynomial function. All right, everybody, so what we're going to do, because this is factored already, we're going to set each factor equal to 0 and solve. Now, keep in mind, this factor is raised to the power of 2. I will not set each of those factors equal to 0. I'll just take one copy. So just x minus 2 set equal to 0, right? I know x minus 2 quantity squared means x minus 2 times x minus 2, but it's redundant to set x minus 2 equal to 0 twice. So just take one copy. And then we'll have x plus 3 equal to 0, and of course 7x minus 1 is equal to 0. After adding 2 to both sides, you get x equal to 2. After subtracting 3 from both sides, you get x equal to -3. Let's add 1 to the right side, and then let's divide by 7. So these are your zeros. 2, -3, and 1/7 are the zeros for this polynomial function. Now, there is some terminology that we need to introduce here, and that is the terminology of the multiplicity of a zero. Notice that x minus 2, this factor, is raised to the power of 2. So, in essence, 2 is a 0 2 times for this function. This concept of multiplicity of a 0 speaks to how many times a particular number is a 0 for that function. So, because this factor is raised to the power of 2, you and I know there's 2 copies of this factor, like we mentioned earlier. So because of that, we say this 0 here has multiplicity 2. Notice this factor has a power of 1. I know it's invisible, but we understand the power to be 1. That means -3 is a 0 of multiplicity 1. Likewise, this factor is raised to the power of 1, so 1/7 is a 0 of multiplicity 1. It is common practice for us to list the zeros of a polynomial function as well as their multiplicity. So what we'll do is we'll say 2 is a 0 of multiplicity 2. And then negative 3 and 1/7 are both multiplicity 1. Okay? Now notice this. If you count all the multiplicities, if you count all of the zeros and their multiplicities, how many zeros do you count? So count this 0 twice because it has a multiplicity 2. So 1, 2, 3, 4 zeros altogether. 4 zeros altogether counting their multiplicities. 4 zeros, and what degree was this function? This function, you'd have to add the powers to find the degree. 2 plus 1 plus 1 is degree 4. The polynomial was a degree 4 polynomial, and then it ended up having 4 zeros. It was degree 4, and it ended up having 4 zeros, counting multiplicity. Please notice that relationship. All right, guys, find and state the multiplicity of each 0 for this polynomial function. X to the 4th power minus 5x cubed minus 6x squared. This is a quartic, because it's degree 4, it's a quartic trinomial polynomial function. All right, everybody, in order to find the zeros of the function, we need to solve the polynomial equation. So, just like before, we need to set the equation equal to, or the function, excuse me, equal to 0, and then solve. All right, so there we have it. Let's solve by factoring if we can. Let's factor out the GCF of x squared, leaving you with that trinomial as a result, which will factor as x minus 6, x plus 1. All right, let's set each factor equal to 0 and solve. All right, for x squared equal to 0, just take one copy, right? Just one copy only. So x is equal to 0. But you will have multiplicity 2. Notice the exponent that's on that factor, degree 2. After adding 6 to the right-hand side, you just get x equal to 6. Subtracting 1 gives you x equal to negative 1. Both of these have multiplicity 1. Multiplicity 1. Let's count all of the zeros and their multiplicities. You ready? 1, 2, 3, 4. And the degree of the function is 4. The number of zeros is the same as the degree of the polynomial function. All right, in set notation, it's 0, multiplicity 2, 1, multiplicity 1, and negative 1, multiplicity 1. All right, good job, you guys. Okay, so what kind of polynomial equation is, or function is this? Well, it's cubic because it's raised to the power of 3, and there's 1, 2, 3, 4 terms. So we would just call it a cubic polynomial function. All right, in order to find the zeros, we need to set the function equal to 0 and solve the polynomial equation. So here I go. I'm going to set the function equal to 0 now. All right. I would even invite you to pause this video and try to solve this polynomial on your own. Try to use factoring. Because there's 4 terms, try to factor by grouping. All right, so I hope you tried that. What I'm going to do is I'm going to group the first 2 terms together. I always put a plus sign in between my 2 groups. Always, always, always. And I keep the sign in front of the term with the term. So keep the negative sign with 12x. Remember, there's more than one way to group these terms, right? So the GCF in this first group would be 3x squared, leaving you with x minus 2. And then factor out a negative 12 here, leaving you with x minus 2. The common binomial factor is x minus 2. And what remains is 3x squared minus 12 is equal to 0. You could set each factor equal to 0 right now or continue to factor. I'll continue to factor. The GCF here is 3, so I'm going to factor out the 3, leaving you with x squared minus 4 is equal to 0. This is a difference of 2 squares, so we'll continue to factor that as well. So then you have, I'm going to put the 3 out front, okay? 3 times x minus 2. And then here is x plus 2 times x minus 2. That's how you factor the difference of 2 squares. So there we have it. Now I'll set each factor equal to 0 and solve. I will not bother to set 3 equal to 0 because that's silly. 3 is not 0. It's not a variable factor. It's a constant factor, so I'll disregard that. Notice that you have 2 copies of x minus 2. I'm not going to set them each equal to 0. I'll just choose one copy only. And then, of course, x plus 2 is a different factor, so I'll set that equal to 0. All right, so when you solve for x, you get 2 and negative 2. Let's use set notation for our solution set. So 2 is a 0. And this is multiplicity 2 because the factor x minus 2 showed up twice, okay? And then negative 2, this is multiplicity 1. If you count the zeros and their multiplicity, I count 1, 2, 3. And our function, we mentioned it in the very beginning, that our function is degree 3. It's cubic. So again, the number of zeros matches the degree of the function. Now this one's going to be interesting. Find and state the multiplicity of each zero for this polynomial. What degree is this polynomial? If you take the leading terms only, x squared and x squared, and if you multiply them, like if you decided to distribute, you would get x squared times x squared, x to the 4th. So this is a quartic or degree 4 polynomial. So then if it's degree 4, I expect to get 4 zeros. Now some of those zeros might be redundant, meaning may have multiplicity more than 1. But counting all the zeros and their multiplicity, we should have 4 at the end of the day. All right, so here we go. What we're going to do is we're going to set the polynomial equal to 0 and solve. All right, ladies and gentlemen, this is what we have. So notice that this does not factor further, and a sum of 2 squares is prime, so that'll never factor. So then I'm going to go ahead and set each factor equal to 0 now, okay? Because they don't factor. Neither of them factor. Okay, here, for this first factor, for this first equation, I'm going to subtract 9 from both sides. And then I'm going to take the square root of both sides. The square root, I'm using the square root property. So I want you to catch this. The square root of the left, the square root of the right. The square root action is the inverse operation of the squaring action, meaning they're opposites. So it just leaves you with x. And then the right-hand side, whenever you take the square root, you have to use a plus or minus symbol. And watch this. The square root of 9 is 3. But because there's a negative underneath the square root, that generates the imaginary unit I. So then there are 2 solutions here, positive 3i and negative 3i. They're 2 different solutions, and they're both non-real, or you can say imaginary. Now over here, for this equation, because it doesn't factor, I'll use the quadratic formula to solve for x. All right, so the quadratic formula will say that x is equal to positive 2 plus or minus the square root of negative 2 squared. Let's see if I can fit all this in here. Minus 4 times 1 times 5. All right, I did it. And then don't forget, all over 2 times 1. Okay, so simplifying this, you'll get 2 plus or minus the square root of 4 minus 20 all over 2. And continuing to simplify, you'll get x is equal to 2 plus or minus the square root of negative 16 all over 2. Don't forget, all over 2. This will be 2 plus or minus, the square root of 16 is 4, and the negative underneath the square root generates I. Notice that every term is divisible by 2, so I'll divide everybody by 2. 2 divided by 2, basically divide this 2 into this term and divide the 2 into that term. And so when you do that division, you get 1 plus or minus 2i. So the solutions for this equation are also imaginary. They're also non-real, all right? So our final solution set will be written as follows. Plus or minus 3i, comma, 1 plus or minus 2i. Now, all of these zeros have multiplicity 1, okay? Let me write that down. All multiplicity 1, okay? I want to make sure that you understand what your four distinct zeros are. One of them is positive 3i. The other one is negative 3i. Another one is 1 plus 2i, and then finally 1 minus 2i. Those are 4 zeros, and remember our function is degree 4. So there's 4 distinct zeros, 4 different zeros. Now, there's something to be said about how these imaginary zeros appear. Here, these are called conjugate pairs. Conjugate pairs. Positive 3i, negative 3i. 1 plus 2i, 1 minus 2i. These are called conjugate pairs. And what is true is, you know how we called these imaginary earlier? You can also say they are complex. Whenever your solutions are imaginary or complex, they always show up in conjugate pairs. So in summary, for any polynomial function with real coefficients that has a 0 of a plus bi, then the polynomial will also have a 0 at a minus bi. Remember, a conjugate pair or a conjugate just changes the operation. So if it's addition, then it's subtraction. That's what we mean by a conjugate. Okay? So whenever your solutions are conjugates, they always appear as conjugate pairs. So if 2 plus I is a 0, 2 minus I is also a 0. If 5 minus 3i is a 0, then 5 plus 3i is also a 0, and so forth. Check out this short example. Consider a polynomial function with real coefficients and zeros at, now pay attention, negative 5i and 3 plus 7i. What are the other two zeros for this function? Well, we just read that if a polynomial function has a 0 of a plus bi, the other 0 is a minus bi. So the fact that they told us that negative 5i is a 0, that implies that positive 5i is also a 0. Furthermore, when they tell us that 3 plus 7i is a 0, that means we are guaranteed to have 3 minus 7i as a 0 as well. Sometimes this is called the conjugate zeros theorem, okay? All right, so here's the last example for this section. What degree is this polynomial function? Can you think about that for a minute? If you want to pause the video, you can. Tell me, what is the degree for this polynomial function? All right, I hope you said degree 6. So this factor is degree 4, right? So if you were to distribute x plus 3 to the 4th power, your leading term right here would be x to the fourth power. So imagine x to the fourth power being distributed now to x squared. In other words, here I can write it out, x to the fourth power times x squared. Those are your leading terms being multiplied. You would have x to the sixth power. So because this is a polynomial function of degree 6, we expect to have 6 solutions or 6 zeros, of course, counting multiplicity. All right, I'm sure you know what to do by this point. The zeros for the polynomial function are the solutions for the polynomial equation. And so I'm taking the function, I'm setting it equal to 0. And it's already factored, right? It's already factored. This is fully factored. Here, this trinomial does not factor any further, so I'm going to use the quadratic formula for this guy. For this factor, I'll just take one copy only, and set it equal to 0. You can see right away that when you subtract 3, you get x equal to -3. We don't want to lose that. So this is one of your zeros, and it has multiplicity 4, right? Multiplicity 4, all because of that power. Okay, so we're going to have to spend some time here. We're going to use the quadratic formula. X is equal to +1 plus or minus the square root of -1. Okay, that's kind of sloppy here. Hold on. -1 squared minus 4 times 1 times 5 all over 2 times 1. So then x would be equal to 1 plus or minus the square root of -19, because this is +1 minus 20 all over 2. So then x is equal to 1 plus or minus. Now, the square root of 19 does not simplify, but the negative underneath the square root produces I. So I'm going to write I and then leave it as the square root of 19. Don't forget all over 2. All right, so our final solution set will be written like this. So it'll be -3, and this is multiplicity 4, right? And then it'll be 1 plus or minus I root 19 all over 2. And I'm going to put multiplicity 1. This is not multiplicity 2. These are two different zeros. One is 1 plus I root 19 all over 2, and the other one is 1 minus I root 19 over 2, okay? So when you count all the zeros, including their multiplicity, you get 1, 2, 3, 4, and then 5 and 6, okay? 6 altogether, and notice we said in the beginning, this polynomial is degree 6. Once again, the number of zeros matches the degree of the polynomial function. This concludes our lesson, but the main thing I want to leave you with is notice that every single polynomial was either factored already or it could be factored. We are heading into deeper into chapter 2, where a lot of the polynomial functions are maybe cubic or quartic or quintic polynomial functions, and they cannot be factored, and they're not factored. So you and I are going to have to do some learning. It's going to be a lot of fun. I'm going to do some learning on how to find the zeros for those kind of polynomial functions. So stay tuned for that in the next few lessons that are coming your way. All right, catch you later.